Good afternoon and good morning, everyone. My name is Yalu Xu. I'm the research fellow at Institute of Earth Science, Academia Sinica in Taiwan. Today is the second talk of our workshop series. Today we will have Dr. Jim Mori from Kyoto University. And this is a part of the workshop series organized by SZ4D. SZ4D is the international component of SZ4D, and it's a coordination network of working toward building an international community studying subduction known geohazard. And this is the mission of SZ4D. And you guys can look at the screen. I'm not going to talk about the detail. So on this slide, we just provide the QR code. If you have any suggestions or for the workshop and the topic, you can scan the QR code and give us some feedback. And on the right, there's a demographic survey. We wish that you can actually spend some time to help us to improve this webinar series. Without further ado, let me introduce our speaker, Dr. Jim Mori. And Dr. Jim Mori earned his master's and PhD degree from Columbia University in the 1980s. And he has extensive experience in the field of volcanology and seismology. And having worked as a volcano seismologist at the Geologic Survey of the Papua New Guinea from 1984 to 1988. He then spent about 10 years with USGS before moving to the Kyoto University in 1999. And Dr. Mori's primary research focus on the physical mechanics of larger earthquakes and volcano eruption. And he has studied significant events around the world, including the 2016 Kumamoto earthquake, 2015 Gokha earthquake in Nepal. And he also served as a co-chief scientist for Japan Trench Base Drilling Project after the 2011 Tohoku Oki earthquake. Today he's going to share insights on fault friction derived from 3 larger earthquakes. Please join me in welcoming Dr. Jim Mori.
Hey, thank you, Yaro. Let's see. Okay, so can you see the slides? Okay.
Yes.
Yes, perfect.
Okay, well, I'd like to thank the organizers for giving me this opportunity to talk about some projects I've worked on over the years, over a long time of a lot of years doing some of this work on temperature measurements from large fault zones. Just start out with a little bit of old history. When I was a graduate student in the 70s and 80s, there was really a lot of interest in the stress levels on faults. We all learned that you could calculate the stress drop of earthquakes from the seismograms, but it was much more difficult to calculate the absolute level of stress. And that's what we really wanted to know. You know, what is the stress level when an earthquake happens? How close are we to a next earthquake from the stress level? And the stress level is tied very closely with friction. Essentially, high stress on a fault means high friction, high frictional stress. And low stress means low friction. And so when I was a student, one of the big questions that was just always discussed about a lot of workshops and a lot of projects was the level of stress high on the fault? Was it kilobars, or was it low on the order of 10 to 100 bars? A level that's sort of equivalent to the stress drop of an earthquake. So in other words, was the stress on the fault very high and the stress drop was only a part of that? Or was the stress on the fault fairly low, and when an earthquake happened, it actually released almost all of the stress? So this is one of the sort of ongoing questions, and still people are interested in this. We don't really have a clear answer to that, but some of the measurements we did on temperatures of faults, I think, give us a lot more information about this issue. When we talk about friction, we all learn, at least I learned in seismology class, about Byerlee's law. And friction was presented in terms of the coefficient of friction, mu. And the coefficient of friction is the ratio of the shear stress to normal stress that's needed to make two surfaces move, to actually be able to sort of push it. And so this ratio of the shear stress to the normal stress is the coefficient of friction. And Byerlee summed up a lot of rock mechanics experiment and found that the data pretty much lined up on this slope of mu equal to 0.6. And this is a summary of lots of different experiments, and it's independent of rock type, independent of the roughness of the sample, independent of the temperature, as long as it's not too high. And so really seen from these experiments that the friction of rocks was about the same, no matter where you went, no matter the type of rocks. And so people pretty much believe this, that the friction of rocks, the friction of sliding rock surfaces together was had a coefficient of friction of about 0.6. That's very reasonable, and it sort of matches up with some sort of everyday observations you make, things like the slope of sand piles or other frictional constraints that sort of show that, you know, it takes about 0.6 times the normal stress of force to be able to move an object or to overcome the friction. One of the consequences of this relatively high friction is that you would generate a lot of heat if you would measure, if an earthquake happened at this level. And here's just an example of some sort of order of magnitude calculations of the temperatures that you might expect from large earthquakes. So here's the temperature, and here's the magnitude. And of course, it depends on the shear stress, which are these diagonal lines. And it depends a lot on how thick is the fault zone. If the fault zone is very thin, like 1 millimeter, all of that heat is concentrated, so the temperature is very high. If it's 1 centimeter, the heat can spread out over a large area, so the temperature is low. But the bottom line is, for a large earthquake, which means slips of several meters, maybe up to 10 meters, and at the sort of lithostatic stress, sort of the normal stress of maybe 10 kilometers depth in the earth, you get very, very high temperatures. I don't know, you might not be able to see this, but this is 10 to the third, 10 to the fourth, 10 to the fifth. So 1,000 or 10,000 degrees if the fault zone is 1 millimeter. It's if the fault zone is 1 centimeter, it's order of magnitude lower, but still hundreds, thousands, 10,000 degrees. So just sort of this very simple calculation said, if the coefficient of friction is around 0.5, 0.6, 0.7, you're going to be generating a lot of heat when you get a large slip, a large earthquake. And that amount of heat should actually melt the rocks. So if this is all consistent, then fault zones should be made up of mostly melted rocks, especially if you have repeated earthquakes. And we do see some melted rocks, pseudo-tachylite sometimes, but they're actually pretty rare. Rick Simpson says probably less than 10% of the fault zone rocks he's looked at contain pseudo-tachylites. So the melting of rocks is not pervasive. And so if the friction is so high, you know, what is happening to all this heat that should be generated? Another consequence of very high friction is that if you have a fault with repeating earthquakes maybe every several hundred years, there should be quite a bit of residual heat left. The rocks can actually keep the heat from you know, dissipating, or not dissipating, but spreading out too much. And so if you measure the heat flow, there should be a peak right over the fault compared to off the fault zone. This is some heat flow data from the San Andreas fault, and essentially it's zero. There's sort of this one high point here, but there is no strong heat flow anomaly over the San Andreas fault. which is what you would expect if the fault friction was so high and you generated so much heat in repeated earthquakes. So anyways, this is what's called the San Andreas fault heat flow paradox, or San Andreas fault heat paradox. And this was talked about a lot, especially when I was a student, and people were essentially divided into two camps. There was the high friction or high stress people who thought that the friction on faults was about 0.6 or 0.7 compared to low friction, which was maybe about 0.1. And the high friction people pointed to Byerlee's law, to the rock mechanics results. And they said the reason we don't see the high heat flow across a fault is because there's water flowing underneath or in the ground, and that sort of washes away the heat flow, washes away the heat. The low friction people said that, well, the friction is probably low because we do not see heat flow. We do not see pseudotacholites. We do not see melted rocks on the fault. And so they said that that means that the faults are low friction or low stress. I'm not going to discuss this today, but both groups also pointed to this argument of what's the angle between the maximum compressive stress and the orientation of the fault. And you can actually use that both ways to argue for both high friction and low friction. I got involved, or I got interested in this problem after the 1992 Landers earthquake. And there was this big fault, probably the best fault that's seen at the surface for many years in California. You can see it extending for several tens of kilometers and had about 6 meters of right lateral offset and about 1 meter vertical. And we were talking about this high stress, low stress problem one day at lunch, and Tom Heaton said, well, you know, if it really was high stress, you should be able to just feel the heat. I mean, there should be so much heat left over that you can, you should be able to measure it very easily. And I said, yeah, that's probably right. That sounds interesting. So I went out to the fault and I put my hand on the fault and it wasn't very hot. And so I thought, well, you know, is that evidence for a low friction fault? And at the time, I didn't think that was a ridiculous statement to make. Just as an aside, I had been at the Pinatubo eruption in the Philippines the year before, and there was a pyroclastic flow that came near our observatory and probably had emplacement temperatures of around 300 or 400 degrees. But we always took reporters out to that site because you could put your hand on the deposits and feel the heat. And that heat was, you know, it stayed warm for several weeks or months. So rocks can sort of keep the heat fairly often. So, so going to Landers and not feeling heat, I thought was significant. The first time that we actually could make a good measurement, though, was probably about 10 years later in the Chichi Taiwan earthquake. And that was a magnitude 7.6. And the notable feature of this earthquake was it had very clear fault offset for along about 50 to 70 kilometers of fault with offsets of maybe 4 to 8 meters. So very large offsets close to the surface, which means they're very accessible to temperature measurements or to studying the actual displacements on the fault. Lots of times earthquakes are fairly deep, 10 or 20 kilometers, so it's hard to get access to the actual fault zone. But this was a good shallow fault with large displacement. And so it really gave us the first opportunity to try to make these temperature measurements. Here's just a photo of a spectacular fault offset along the river. So this waterfall was caused by the fault scarp. So this is a hanging wall up here, and this is the footwall here. And there was about 6 meters vertical offset on the fault at this place. And pretty soon after the earthquake, there was a big project to drill into the fault, the Chalangpu fault drilling project. And it was very successful. The site was up at the northern end of the fault, and they drilled a vertical hole which penetrated the fault at about 1,100 meters. And so there's a lot of good, interesting results, getting a sample of fault, looking at the fault, looking at the fault zone. Our part of the project, though, was to measure the temperature in this borehole across the fault here to try to get an idea of, is there any residual heat? Is there anything left over from the presumably very high friction or presumably friction that occurred during the fault that we can see several years later when this borehole is actually drilled. Here's a diagram of the fault slip done by Kofung Ma of the Chichi earthquake, and this is where the drill hole was. And it was in an area of probably about fault slip of maybe 4 or 5 meters. Of course, we'd like to be in the area of much larger faults, 7 or 8 meters, much larger slip, but it takes a lot more money, takes a lot more time, and even getting to 1 kilometer depth was a big effort. So that was the best we could do, is to drill the 1 kilometer deep drill hole into the fault zone. At that time, there weren't any commercially available temperature sensors. So we had to go and build our own. And so we built this very long, heavy thermometer, essentially. So it was a very large, heavy instrument. There were 2 temperature sensors in it, one at the top, one at the bottom, and there was data logging in there. But it was big and heavy. It took 4 or 5 people just to carry it. And we needed a big crane just to drop it down into the hole to get to measure what the fault zone temperatures was. So it was a very cumbersome and big effort to try to even just measure the temperature to the accuracy that we wanted at that time. Okay, so this is actually what we measured. And so here's a plot of depth and temperature. And you see as you go deeper, the temperature increases. So this is just the ambient heat flow, the ambient fault zone, the ambient heat gradient that increases with depth. If you look very carefully, you can see that there's a small increase as you go right over the fault zone. This is the fault zone here. If I didn't color it in blue, you probably couldn't, you would just barely be able to see it. But I think this is real. And so this is what we're really looking for. There's four data streams here because, as I said, we had 2 channels of temperature measurements, and we lowered the instrument and we brought it up. So we had going up and down for two channels. So there were 4 data streams that we had. And all of them had this small increase right over the fault zone. And so we were very happy. We actually thought we could see something across the fault that might be related to this residual heat from the earthquake. To use that data to actually calculate the friction, to calculate the heat, you can model just the diffusive heat using this equation. So the temperature as a function of distance away from the fault and of time can be given by this simple equation. And so this is an equation that you can find in geophysical textbooks because it's used for calculating the temperature from emplacing a volcanic dike. So if a dike suddenly gets in place, you can calculate with time and distance from that dike what the temperature should be. And it's an exponential, distance exponentially decay, the temperature exponentially decays with distance away from the planar source. And the things that you need to know is just the time, the distance, and the heat diffusivity. You know, how fast does the heat spread out in this particular medium? So we use this equation to calculate the actual heat. So S is the heat source, and so that's what's unknown. And also we didn't know the heat diffusivity, but just 2 parameters is relatively few to actually use this equation. Just to calculate what these heat sources would look like, 1 week after an earthquake, the heat would be, or the temperature would be about 5 or 6 degrees within maybe a few tens of meters from the fault. and depending on the coefficient of friction. So if it's a coefficient of friction of 0.1, it'll be about 1 degree. It's about 5 degrees if the coefficient is 0.7. Of course, we can't get to the fault 1 week. If we drill maybe 1 year after the earthquake, the temperature now is much smaller, but still there should be about temperature anomaly of somewhere between 0.7 or 0.1 to 0.7 degrees within about maybe 30 or, well, not 30, within about 10 or 15 meters from the fault. So this just shows that the diffusion of the heat as it spreads away from the fault zone. This is that same equation, and so we want to calculate the amount of heat, S, that goes into the equation, and we want to calculate this coefficient of friction. And this is what we started out looking for. And again, it's simply the shear stress divided by the normal stress. So if you have the shear stress and the normal stress is just a lithostatic stress with a correction for the pore pressure. And then we can back out and actually calculate how much heat was generated by the temperature that we measured. And if you do that, the answer is this, that we get a shear stress of about 1.2 megapascal. Actually, I can't see the units. Sorry. Okay. About 1.2 I can't see the units. What is it? I forgot what the units are. So anyway, so this is the amount of heat that we calculated was generated by the earthquake in the small fault zone, which produced the anomaly. Okay, so here's that same data I showed in the other slide, but the data is now turned around so that this is distance from the fault zone, which is 0, and this is temperature, and this solid black line, this thick black line, is those 4 data streams averaged together. And so the heat anomaly we saw was about 0.05 or 0.06 degrees. So very small. We actually didn't get to the fault until about 4 years after all of the drilling and, well, getting the proposal funded and all logistics took some time. So this is what we saw 4 years after the earthquake, an anomaly of about 0.05 to 0.06 degrees across the fault with a width of maybe 20 or 30 meters. And if we use that equation I showed before to calculate what the coefficient of friction is, this line is for a coefficient of friction of 0.1. The bottom line is for a coefficient of friction of 0.6. So the best fitting line is about 0.08. Anyways, it's about 0.1 or less. It's very small. And that was not, well, it was surprising, but not really surprising because those are the kind of numbers we sort of expected. But this is probably one of the first really good direct measurements of a coefficient of friction. And so we get this number of maybe 0.08, which is much smaller than the Byerly level of about 0.6 that I discussed before. So yeah, so what is this number? So this number, this TCDP temperature measurement, gave us a coefficient of friction of 0.8. And Byerly's law said that the rock friction should be about 0.5 to 0.7, so much, much smaller, about maybe an eighth or a tenth of what that is. Just other examples of coefficient of friction, rubber on concrete. So a tire on a road has a coefficient of friction of about 1. Rubber on concrete wet is about 0.3. So when you put water on there, the coefficient of friction decreases a lot. Steel on ice, so ice skating, has a coefficient of friction of about 0.03. So this coefficient of 0.08 is actually pretty small, much smaller than what we expect from rock mechanics, and not quite as small as ice skating. But but it's very, very slippery. It still slides quite easily from this number that we got. Okay, so that was the first measurement that we made, and we got this low friction coefficient of friction of about 0.08. Right about this time, there was also a workshop that we held, an ICDP and SCEC workshop, to try to repeat this experiment on more faults. So we spent a couple days, these are the conveners of the workshop, and actually made a plan and discussed in fairly detail the scientific issues, the technical issues. And so we had, what is that? We had a lot of good discussions, so we were ready for the next earthquake that we could actually move much quickly. In Taiwan, it took us about 5 years to actually make the measurements. So by then it was 0.03 degrees, so it was very small. But we wanted to try to get a much better measurement, much faster, and much more well resolved. And so this report was good for having discussed the problems once, and then it made it very easy, not easy, but it really facilitated writing proposals immediately after earthquakes to be able to do this again. And that was very timely. So this workshop was in November 2008, and actually in May of 2008, the Wentron earthquake happened in China. And so that was magnitude 7.9. And so that was actually our next target. The Wentron Fault Scientific Drilling Project was a big effort to drill actually several holes along several strands of this large 7.9 earthquake. The first hole, FSSD1, was used for temperature measurements, and that hole penetrated this steeply dipping strike slip fault at about 500 or 600 meters. So it penetrated the fault here, and we were able to make temperature measurements over a period of time for this earthquake. Just in 4 or 5 years, the technology of measuring temperature really improved. So instead of this instrument that we built, they were now commercially available, very small, very lightweight temperature sensors that were just 20 or 30 centimeters. And so we could just put those onto a line and drop it into the hole. And instead of a crane, just a very small winch could be used to make the temperature measurements. So at Wentron, these temperature measurements could be made very easily. And so about 10 or 12 measurements were made sort of on a monthly basis. In Taiwan, we actually only made one temperature measurement. We had only one chance when we could make those 4 runs. But here we were able to make several runs over about a year. Unfortunately, the data was not so great. This is 2 examples in January 2010 and February 2010. And this is the fault zone anomaly, or what we thought was a fault zone anomaly. There's other sort of noise. This thing is here on both, but it sort of changes size. But this is what we thought was the possible anomaly. And it was still pretty small, only about a few hundredths, maybe 0.02 or 0.03 hundredths of a degree. So much smaller than we expected. And actually, it just wasn't very clear. It wasn't very convincing data. This data was stacked over several different measurements, and we could get a nice shape, but this actually was not so convincing because this width actually wasn't quite right for this sort of 2 or 3 years after the earthquake. And also this width didn't seem to increase with time. You would expect it to kind of flatten and get wider. And so this was a little bit hard to interpret, but sort of the main result was simply the anomaly was small. It was less than, or it was about 0.02 degrees. And this gives a very small coefficient of friction. But the bottom line is it wasn't big. If the coefficient of friction was 0.4, 0.5, 0.6, we should have seen quite a large heat flow anomaly. And we didn't see that. Maybe the fault was distributed over several faults. Maybe there was some fluid flow. We really don't have a good answer now, but the main result from this experiment was simply we did not see a large anomaly. So we did not see anything that indicated that there was high friction. So probably this is more consistent with a low friction. Okay, the third chance was the famous Tohoku earthquake in 2011. And following that earthquake, we had a very large IODP drilling project called JFAST, which was actually able to get to the fault very fast. The earthquake was in March 2011, and this expedition sailed in April 2012. So just a year and 1 month after the earthquake, we managed to mobilize the drill ship, get all the project going, and so we were able to make a very, very fast measurement, and that's why it was called JFAST. A big IODP project. There were scientists on board from 10 different countries, geologists, geophysicists, geochemists, and biologists. So it was a large fault to investigate a large project to investigate the fault, and the temperature measurement was just one part of this very large project. This was a place of really huge slip, which was one reason we really wanted to go there. It's the largest slip ever recorded for an earthquake. It was probably something over 50 meters on the shallow part, the toe of the subduction zone. And of course, that very large slip is what generated the huge tsunami, which was up to 40 meters in some areas. So it has relevance, obviously, for earthquake physics, but also it's very important just to understand for generating the tsunami. What was the slip? What's sort of the frictional measurements? What really allows a fault to move such a great distance and so cause this large tsunami? This is the drill site. Here, the JFAST drill site on some seismic reflection data. And so what you see here, this very dark line that sort of steps down in a Horsten-Graben structure, this is presumably the Pacific plate, or actually the top of the Pacific plate, probably the boundary between the sediments and some harder rock of the Pacific plate as it's being subducted to the west, to the left here. And so this is the trench, the Japan Trench, and this was the drill site that we picked to try to reach the actual fault zone, the actual subduction fault zone. Again, we'd like to be way off to the left here at some, 5 or 10 kilometers depth, but you can't drill that depth easily. And so we were limited to about 1 kilometer drilling. And so this was picked as the drill site. As you go closer to the trench, things seem to get very complicated. There seem to be a lot of splay faults. There's this Horsten-Graben structure. And so we wanted to be in a relatively simple area where we thought we understood the fault structure, where maybe, hopefully, there was only one fault. And this really was the découlement. This really was where this very large slip of 30, 40, 50 meters occurred during the earthquake. There was a lot of drama. There was a lot of problems and a lot of successes, mainly due to this water depth. The water depth of just getting to the ocean floor was almost 7,000 meters. So that's a pretty long piece of pipe, pretty long and pretty heavy that you have to deal with just to get to the ocean floor to start drilling. And the first month, there was just lots of problems, which we actually did manage to overcome just 2 days before the end of the expedition. So 2 days before the end of the scheduled ship time, we actually managed to get to the fault zone and brought up this core number, number 10 of the fault zone. And the geologists on board were just ecstatic. They said, yes, this is the fault zone. This is the scaly fabric that was seen. And so we managed to get a sample of fault from about 821 to 824 meters. And this probably was the fault zone. It may not have actually contained the actual slip zone from the earthquake, but it probably was the real fault zone. So we can take this as being fault zone material that we collected. We actually, here's just a close-up of the brown pelagic clay, the fault gouge that was recovered. Because of the reaching the fault zone at only 2 days before, we weren't able to actually put in the temperature sensors to make the temperature measurements at that time. One thing that was done, though, is that fault zone material was taken back to the laboratory, and this sort of rotary frictional experiment apparatus was used by Kotaro Ujiie to measure the friction, measure the coefficient of friction of this fault zone material. And here's just some data that he took. He used this rotary machine so that very large displacements, maybe 20, 25 meters. So getting close to what the actual displacement was during the earthquake. Also, it's a very high velocity machine. So probably these experimental conditions were close to what happened during the earthquake. And this is the answer that he got. He got a coefficient of friction, coefficient of dynamic friction of about 0.1 from this material that we collected from the Japan Trench. Above is material collected from the Nankai, which is also low, but it's about 0.2. So this was probably a very important and one of the first real measurements of coefficient of friction from an active fault zone that was taken from the sample that we collected, and very low friction. The reason it was low friction is probably because of the high smegtite content. This is X-ray diffraction material, and there's this large peak from the Japan Trench material for the smegtite peak. I said we couldn't get the temperature measurements done at the time, but we were given a second chance. And a few months later, we were given about a week of ship time to actually try to get the temperature sensors in. And this time things went very smoothly. We drilled a hole with no coring, just straight down into the fault zone. And that was drilled in about 2 days. And the string of about 40 temperature sensors was put down into the hole very quickly. So we were very gratified. And here's the wellhead for that that installation. And so this was done in July 2012, being able to get the temperature sensors in. Once the temperature sensors are in, you have to get them out. And to get them out, we use this ROV, this Kaiko, which is one of the few instruments that can go, few ROVs that can go down to that length of that depth of water. And as usual, things didn't go smoothly. We went to try to retrieve the data in February 2013, but we couldn't find it. We couldn't find the site. We had bad weather, we had navigation problems, and so we came back with nothing after that cruise. But then we went back again in April, and we found the site, and we were able to retrieve the temperature sensors in 2013. So here's the data. Here's an example of the data that we collected. Again, here's depth, here's temperature, and here's just the heat flow gradient that we measured. And here's the blow up of this very lower section, and the fault is way down here at the bottom. And you can see this anomaly of about 0.2 degrees at the very bottom. We don't have the anomaly on the other side on purpose because we only put temperature sensors on one side of the fault, because we heard there might be afterslip, there might be movements on the fault, and we didn't want to take the chance of losing the drill string, temperature string completely. So we measured the temperatures just on one side of the fault. And here's that same data, but now this is depth and this is time, and the colors show the temperature, the temperatures. And so when the temperature string was first put in August, the temperature was very cold. And then gradually over a few months, the temperatures increase. This is just because the temperatures are very low, because ocean water is filling the hole, and it takes about 2 or 3 months for the hole to come back to the equilibrium temperatures. So what we really want to look at is this area here. So a few months after the temperatures sensors were put in, and there was a large aftershock on 7.3 on December 7th, and that kind of upset the whole system. It probably just shook the water column, it shook the area, and so the temperatures changed. And this is actually valuable data, but it kind of upsets the whole system. So the interesting data is here, is right before this large aftershock, but after the temperatures had equilibrated. And we can see that there was a temperature increase of about 0.2 or 0.3 degrees across the fault. Here's the fault. I say we didn't measure all on the opposite side, but we did measure sort of 2 meters on the other side of the fault. So we have a little bit of data on the other side of the fault. Okay, and this data was modeled by Patrick Fulton, and here's the data for that time period from about August to December, and here's the model. And again, temperatures of about 0.2 to 0.3 degrees, and that gives a coefficient of friction of about 0.1. And we are very happy to see that number. Again, that's very consistent with the laboratory, the direct measurements of the coefficient of friction from the laboratory, which was also about 0.1. And so this completely independent temperature measurement also gave us a coefficient of friction of 0.1. And so we were very gratified, very happy to see that. And so that's the third temperature measurement and rock mechanics, and so that was 0.1. So that's sort of the story. So we made 3 temperature measurements, and all of the derived coefficient of frictions were very low, on the order of about 0.1. And so it's not consistent with Byerlee's law. Of course, we're measuring different things. Byerlee's experiments were especially measuring static friction, just how much to make the sample move. And that's probably good, but we're measuring dynamic friction. We're measuring the amount of shear to normal stress that happens to generate the heat. So that's the heat generated during the whole rupture while the fault is slipping. And so that's the dynamic friction that's creating the temperature, that's creating the heat. Excuse me. The static friction, of course, from Byerlee's law is much different. And that has to be high. I mean, we have mountains and we have earthquakes. If static friction was so low, we couldn't sustain mountains, and we couldn't sustain deposits of mountains, and we would never build up enough stress to have earthquakes. So static friction has to be high. But the dynamic friction, the friction levels on the large faults that are moving 10 meters or 20 meters has to be low. And that's also low heat, and that's actually also consistent with landslides that we see very large, low friction slips. Okay, so conclusion. As I just said, static friction on faults has to be high because we have earthquakes, we have mountains, and it's probably on the order of 0.5 to 0.7. The dynamic friction from these temperature measurements, that's the friction when the large slip is actually happening, is something that the friction must drop during after the earthquake starts. And there's lots of mechanism, thermal pressurization or lubrication. Lots of people presented mechanisms for friction drop once a fault gets going. The heat that's produced on the fault during the earthquake is the dynamic friction. So this actually gives a good explanation for the San Francisco-San Andreas heat flow paradox, that the heat is generated by the low friction dynamic friction, but the static friction that we measure in laboratory or we measure from rocks still has to be high. Okay, so anyways, this is sort of results of, I don't know, 20 years of measuring friction. And this probably seems, what I say, obvious now. But when we started this 20 or 30 years ago, we really didn't know a lot of this. And so it's sort of gratifying to kind of come this long journey of measuring these friction from temperature and from other measurements. So I think I'll stop there. Thank you.
Thank you. Thank you, Jim, for the very nice talk. So I think we are open for questions. So I see, okay.
Sorry, I'm seeing one question in the chat from Ruoyan Wang. Does seawater come into the drill hole, which may affect the temperature measurement? How to consider this effect?
Okay, basically we didn't consider it. We just let it equilibrate. So once the cold, well, we saw the temperature increase and sort of level out after a few months. So we assumed that the temperature in the hole had equilibrated. And so that's why I said the time up to that aftershock was what we expected the temperatures to reflect the temperatures of the faults on the temperatures in the borehole. I guess you could actually calculate. You could do a model. Well, I'm sorry. When I say we didn't consider, actually Patrick did consider that. He did consider starting from the sort of cold the cold fault. And so in his model, in his model, he actually did consider it starting from a very cold and then equilibrating later. It doesn't actually match this, but he did consider it starting cold and then getting back to the ambient temperature. By the way, the water temperature at the bottom of the ocean is close to 0 degrees. It's not freezing, but it's very close to it. So the water that goes into the hole is close to 0 degrees. So that's why it's very cold in the hole.
So Julia, are you going to the second question?
Sure. We have another question from Binhao Wang. Thank you, Jim, for the great talk. Biomarkers record temperature rise of several hundreds of degrees. How would you reconcile the low friction observation from heat flow and the biomarker? Actually,
that's not inconsistent at all. Patrick calculated what the extrapolated temperature should have been at the time of the earthquake, just going back in time. And depending on the duration of the faulting, and depending on various other conditions, he calculated that the temperature probably was a few hundred degrees at the time of the earthquake. When we measured it 2 years later, it was 0.25, but at the time of the earthquake, it probably was a few hundred degrees. So the biomarker data is actually very consistent with our results.
Looks like we have another question. From the time of the earthquake, what would be the best time to do the measurements?
Well, if you can get there 1 hour, you should be able to measure very high temperatures. But of course, you need a borehole, and it takes time to drill a borehole. It usually takes even more time to write a proposal to get money to drill the borehole. So that really is the the drawback. We'd like to get there as fast as possible and drill as deep as possible to see, we'd actually like to measure that 100-degree, presumably that 100-degree temperature effect that happens right after the earthquake. And actually, that was why that ICDP workshop was very valuable. So we went through various scenarios about how fast you needed to be there, how deep you should drill to see a good signal. And so having sort of gone through that once really helped with writing proposals, being able to sort of make estimates and say about how fast, about how deep, in order to see an anomaly of a few tenths to maybe a few degrees. And like I said, the problem is the borehole. You can't really make the measurements on the surface. The surface material is usually very weathered, very complicated, and you need to get down to sort of the very simple, sort of clear fault zone area that can preserve the temperatures. And so just measuring the fault on the surface, like putting my hand on the fault's not going to do it. So you need a borehole, and if you need a borehole, it's going to take some time to actually get that process going.
Thank you so much. Currently, we don't have any other questions, so I want to invite our attendees to feel free to type them in the Q&A section below if you have some. And I think we'll give a couple of more minutes just in case people are typing.
If there's no questions, I mean, just I didn't give it in this talk, but I always use the example that this experiment is the same as sliding your hands, and when you rub your hands, it gets warm, and that's because of the friction of your hands. Excuse me, and you can actually make this exact same calculation that we did on the fault for your hands, and calculate the coefficient of your hands from how much temperature increase there is. So if you move your hands, you can feel the heat. So that means there's probably 4 or 5 degrees of temperature increase. And if you do it several times, you probably get about 10 degrees increase. And so if you back out all those numbers, you can actually calculate what is the thermal constraints, what is the stress that you need to press on your hands to get that heat, and what is the skin depth. So this idea that the fault generates heat is actually a very simple idea. And it's exactly the same as just sliding your hands and feeling that heat. So when an earthquake happens, it generates that heat. And if you can measure that heat and measure the temperature, you can back out what the coefficient of friction is during the earthquake.
Thank you very much. Since we don't have any other questions, oh, we do. Okay. Is it useful to measure the friction of an aseismic creeping fault? And thank you for your great talk, Jim, from Chiao Jose Sun.
So you probably can't see. Oh, hi, good. He was on JFast. You aren't going to see any temperature increase on an aseismic fault, because there's no, even for this very large earthquake of Tohoku or Taiwan, where you slip 10 meters, there was a small temperature increase. So if it's slipping aseismically, there may be 1/10,000th of a degree or something like that, but you're never going to measure that. So, to understand friction, measuring aseismic faults is not very useful. But maybe aseismic faults do cause temperature anomalies, but it wouldn't be due to the friction. It would be due to some other mechanism, maybe fluid flows or some other fixed physical mechanism that can redistribute the heat on the fault. So I would say it's probably useful to find something new, but it's probably not going to tell you much about the friction on the fault.
Thank you. We have another question from an anonymous attendee. Does that mean that if you have a permanent installation, you can somehow detect temperature anomalies before an earthquake?
So that was an idea that we had, try to monitor a fault and have an earthquake happen. And then so you're right there to measure the temperature, measure the fluid flow, measure every these things. And these are some of the ideas behind these sort of active fault monitoring. So yeah, that would be exciting. But the problem always is whenever you monitor a fault, you usually don't have an earthquake. You have to wait a long time for an earthquake. But yeah, we'd like to do that.
Great, thanks. From Bin Hao Wang again, fluid might be present in the fault zone. Could you explain how the presence of fluid in this permeable zone would affect the temperature rise at the time of the earthquake and afterwards?
Okay, that's a good question. And that actually comes up a lot. Is there fluid moving through or moving up and down the fault zone that's maybe washing away some of the heat or is really affecting the temperature measurements? Probably, we don't really know, but we assume that even if there is fluid in there, it's actually not moving a whole lot. It sort of stabilizes. So that when you make the temperature measurement, there's water in there, so you're measuring the temperature of the fluid. You're measuring the fluid temperature. But if it's all sort of equalized, it sort of doesn't matter that you're just measuring the fluid, the temperature of the fluid, and that's reflecting the sort of borehole wall. That's reflecting the fault zone temperature. Now, if the fluid is actually moving, that causes a lot of problems. And that was what people always said about the San Andreas heat flow paradox, is that there were fluids moving through the fault zone and that was washing away the fault. We always assume that there isn't a lot of movement of the fluids, and so that our measurements are really reflecting the actual in situ temperatures in the fault zone.
Thanks. We have another question from Chi-Xian Heng. Thank you, Jim. Can we expect the low friction only occurs at the shallow depth of the fault, or is it safe to extrapolate all the way down to the seismogenic depth?
That's another good question. So we never tried, so one of the most, the thing to make these friction and stress measurements, what you really ultimately want to do is do the energy balance for an earthquake. And actually I've done it assuming that this fault friction is representative of the whole fault. But I think that's really a stretch, and that saying that the very shallow friction, shallow stress is representative of the whole 100 kilometers down to 40 or 50 kilometers fault zone is difficult. Maybe Kailing Wong will talk about that in his keynote speech later this week. So I've never been brave enough to extrapolate this measurement to the whole fault zone. But I think Kailing Wong sometimes says that it is representative. So that's an important issue to explore.
Thank you. From Prof. Daya Shanker, how do you tackle submarine landslides while deep ocean drilling?
Do you mean that drilling might induce the landslide, or just the fact that there are submarine landslides? The fact that there are submarine landslides is not a huge problem, because you just would be drilling through the landslide, and it's sediment, and so there might be some drilling technicalities. But if there's a landslide on top of the fault, it's sort of not a problem, because you would drill through that. I don't think the actual drilling which would trigger a landslide. The drilling is, it's just a pinpoint measurement, and so it probably wouldn't induce large enough effects to cause a landslide. At least we hope not. I mean, when we started JFAS, there were concerns that would we actually trigger another earthquake or we trigger aftershocks. But again, these are just sort of really pinpoint measurements or pinpoint drill holes in a fault that's, hundreds of kilometers. So probably even trying to induce an earthquake would be difficult. And actually, it'd be interesting to do, but probably is not something that that we would expect.
Thank you. And our last question is, in the plot of heat flow gradient for the Tohoku-Oki rupture area, why are the sampling points much less before reaching the target depth?
Okay, that's just because each point is a temperature sensor. And so the temperature sensor string, we made it much more dense close to the fault. And 50 meters, 100 meters away from the fault, the temperatures were spaced at much larger distances. And so, you can only have a limited number of sensors. And so you try to put the densest spacing where you hope you'll measure the fault, measure the anomaly. So yeah, that's just a function of what the distribution of sensors is on the string.
Great, thank you. Since we are now just over the hour, I want to be cognizant of everyone's time and thank you, Jim, for such a wonderful talk, and invite all of our attendees to give you a virtual round of applause. And I want to thank all of our attendees for taking their time out of their busy day to come join us for our first virtual workshop. Our next keynote talk will be Whitney Bear tomorrow morning at 7 a.m. PT, which I believe is in UTC will be 2 to 3 p.m. UTC. So we hope to see you there. It'll be the same Zoom link. And thank you and enjoy the rest of your day.
Thank you.
Thank you, Jim. Thank you.
Thank you.
Bye.